I'm going to go through an example of a problem that involves balancing a redox reaction using the oxidation number technique. So here's the equation that I'm confronted with. And in order to make sure that this is an oxidation reduction reaction, I'm going to go through each term, both of the reactants and of the products, and using the rules that we learned in class, I'm going to assign oxidation states to all of the species. As I write this out, you can double check, referencing your rules that I gave you in class, to make sure that I've accurately depicted the proper oxidation states for each of the reactants and products. And once I've done that, I can see right away that sure enough, the chromium has gained 3 electrons, going from +6 to +3, so it's being reduced. And the sulfur is giving up 4 electrons as it goes from 0 to +4. So this represents the electrons being exchanged. Now, in any kind of exchange, the number of electrons being given up and being accepted have to match up. So the first thing I want to do is go ahead and find a common multiple of 3 and 4, and of course that's 12. So it would take 4 chromiums to accept 12 electrons, and it would take 3 sulfurs in order to donate 12 electrons. And so what I want to do then is end up with 4 chromiums, and I go through and I put a 2 in front of the potassium dichromate and the chromic oxide, and I end up with 4 chromiums on each side. And then go ahead and do the same thing for the sulfur. It would take 3 sulfurs in order to donate those electrons, so I need 3 on each side, and of course I put the coefficients 3 in front of the sulfur on the left side and the sulfur dioxide on the right side. The next step in this technique is you look at the rest of the elements and you make sure you balance them. So let me rewrite the equation one last time. And let me place in the coefficients I've already nailed down. And I notice that I've got 4 potassiums on the left side. So to get 4 potassiums on the right side, I put a 4 in front of the potassium hydroxide. But doing that changes the number of hydrogens. So I'm going to need 4 hydrogens on both sides. So I put a 2 in front of the water. Now, very likely, the only other element that I have to check on, oxygen, it's likely that it's already balanced because it's so ubiquitous. It's found everywhere. And that's the way it turns out. If you check on the left side, we've got 2 times 7, 14, plus 2 is 16 oxygens on the left side. On the right side, 4 from the first term, 6 from the second term, that's 10, and then another 6 from the last term. And there we have our balanced equation. So I took care of the electrons being exchanged, and then I started going after each individual element and making sure their atoms also balance.